I want you to close your eyes for just a second.
Oh, we're doing a visualization exercise.
Yeah, just go with me here. I want you to imagine that you are a scientist, but it's the early 19th century.
Okay. Mutton chops, the whole 9 yards.
Exactly. And you're standing in this incredibly muddy quarry somewhere in the English countryside. Your hands are just completely raw from chipping away at this ancient, unyielding stone.
Right.
You're using tools that, by today's standards, I mean, they're basically just primitive pickaxes.
Pretty much.
And then suddenly your tool hits something completely different, not rock, bone. So you clear away the dirt and the centuries of debris, and you manage to haul out this massive, unbelievably heavy, totally bizarre piece of fossilized bone.
A monumental discovery.
But here's the kicker. You hold it up, you wipe the sweat off your forehead, and you realize you have absolutely no idea what you are looking at. I mean, none.
Yeah, you're holding a piece of this ancient puzzle, but the frustrating part is that nobody's ever seen the picture on the front of the box.
Exactly. It's a profound sort of blindness.
It really is. I mean, at that point in history, the very concept of a dinosaur, that word hadn't even been fully articulated yet. You are literally trying to comprehend an animal that defies everything you currently know about biology.
And that sense of profound mystery, that complete shot in the dark, that is exactly where we're starting today.
This is a good one.
We are going to trace the story of one specific creature, a genus of early Cretaceous sauropod dinosaur known as Ornithopsis. And I'll tell you right now, we are not just going to list off a bunch of dry, boring facts about dinosaur bones.
No, we are getting into the mud on this one.
Okay, let's unpack this. We are going to outline the mission here, which is to trace the incredibly complex, highly dramatic, and honestly sometimes just deeply petty history of how this one dinosaur was discovered, named, renamed, and fought over by scientists for literally over a century.
Massive egos, bitter academic rivalries, aggressive renaming campaigns, it's got it all.
But before we get into the 19th century academic flame wars, I think we need a solid anchor.
Good idea.
For you listening, we need to know what the modern scientific consensus actually is. So if we look at Ornithopsis through the lens of 21st century paleontology, what exactly are we dealing with? Let's set the baseline.
Well, when we look at the surviving evidence today, we classify Ornithopsis as an extinct genus of titanosauriform.
Okay, titanosauriform, break that down for us.
Sure. To visualize that, you need to picture the classic sauropod body plan. You know, the massive four-legged giants with the long necks and the long tails.
Like a brachiosaurus.
Exactly like a brachiosaurus. The titanosauriforms were a remarkably successful, globally widespread subgroup of these giants. And Ornithopsis, it was not a small animal.
How big are we talking?
Based on comparisons with more complete relatives, like the famous Giraffatitan, we estimate that the type specimen of Ornithopsis belonged to a creature that was roughly 16 to 18 meters in length.
Wait, 16 to 18 meters? That is, I mean, what is that in feet? Like 50 to 60 feet long?
Yep, 52 to 59 feet is a good estimate.
You are talking about an animal the exact size of a bowling lane.
A very heavy bowling lane.
Just walking around early Cretaceous Europe.
Precisely. You would be looking at an animal that could comfortably peer over a 3-story building. But, and here's the critical caveat, and honestly, it's the engine that drives all the historical drama we're about to discuss. Our entire modern understanding of this colossal animal is based on extremely fragmentary remains.
Right, we don't have the whole thing.
Not even close. We do not have a beautiful, pristine, fully articulated skeleton sitting in a museum hall somewhere. We have pieces.
Fragments.
Just individual bones that have been subjected to intense, almost obsessive scrutiny.
And the name itself, Ornithopsis, that feels like a very specific choice. What does that actually translate to?
The name is the absolute crux of the entire controversy. Ornithopsis comes from Greek. Ornis means bird, and opsis means likeness.
Bird-like.
Yeah. Bird-likeness. It is a heavy, massive dinosaur that was named for looking like a bird. And currently, the only species within this genus that modern science widely accepts as valid is Ornithopsis hulkei.
Which just seems like an incredible contradiction. A 60-foot, earth-shaking reptile being named for its bird-likeness.
I think that's totally counterintuitive.
And that contradiction is exactly why this story is so important for you here. This isn't just a biology lesson. It is a masterclass in how science actually works in the real world.
Absolutely.
We so often get taught that science is this clean, objective march toward the truth. You know, hypothesis, test, fact. But the story of Ornithopsis shows that science is messy.
It's full of blunders.
Blunders, personal biases, huge leaps of logic. So let's go back to the very beginning. Let's look at the first blunder. Take us to 1833. Who is finding the first piece of this puzzle?
So the story begins with a man named Gideon Mantell.
Mantell, a pretty famous name in the field.
Very famous. He was a prominent figure in early paleontology, though he was originally a medical doctor. And in 1833, he was studying fossils that had been pulled from the Tilgate Forest.
Which is part of the Wealden Formation in southeast England, right?
Correct.
And the Wealden Formation is a pretty big deal in the dinosaur world.
Oh, it's foundational. The Wealden Formation is this incredible sequence of sedimentary rocks that perfectly captures the terrestrial and freshwater environments of the early Cretaceous period. It is essentially the cradle of British dinosaur paleontology.
So Mantell is looking through the material recovered from these rocks.
Yeah, and he isolates a very specific fragmented bone. For those who like to track the museum catalog,
I know you're out there.
this piece would eventually be purchased by the British Museum in 1838 and cataloged as specimen R2239.
Okay, so Mantell has this giant stony fragment on his desk. He has to call it something. What does he decide he's holding?
He concludes that he is holding a piece of an Iguanodon.
Okay.
Specifically, he believes it is the quadrate bone.
The quadrate, that's a skull bone, right?
Yes, the quadrate is a crucial part of the skull. It forms the actual joint that connects the lower jaw to the rest of the skull.
Okay, I'm really trying to wrap my head around this. How does a medical doctor, someone who literally studies anatomy for a living, pick up a bone from a 50-foot long-necked dinosaur and say, aha, yes, this is clearly the jaw joint of an entirely different animal?
What's fascinating here is that you really have to put yourself in his shoes. You have to remember the extreme limitations of his era.
Because it's 1833.
Exactly. The word dinosaur hadn't even been invented yet. The concept of an entirely extinct group of giant diverse terrestrial reptiles simply wasn't established.
Right.
What Mantell did know, for a fact, was that there was a large herbivorous reptile in that exact geological area. And he knew this because he and his wife had previously found fossilized teeth belonging to a creature he named Iguanodon.
Right, Iguanodon, because the teeth looked exactly like a modern iguana, just scaled up to monstrous proportions.
Spot on. So his logic goes like this. He knows Iguanodon is in the Wealden Formation. Now he finds another massive, bizarre reptilian bone nearby. He looks closely at this new bone and notices it has these deep cavities, these hollowed-out spaces inside the bone structure.
Okay.
Mantell misinterprets these spaces. He thinks they are what anatomists call a tympanic cavity.
Like the tympanic membrane, the ear.
Exactly, the hollow space in the skull that houses the middle ear.
Ah, okay. I see where he's going. So his logic is, it has an ear cavity, therefore it has to be a skull bone. And if it's a giant skull bone found in the same forest as giant iguanodon teeth,
it must be the jaw joint of an iguanodon.
It's wrong, but it's a very logical kind of wrong.
It is an entirely rational hypothesis based on an incredibly limited data set. I mean, he was trying to fit an unknown piece into the only puzzle he knew existed.
Right. But of course, science doesn't just let hypotheses sit unchallenged forever. And this is where the scrutiny begins.
The plot thickens.
We jump forward about 20 years to 1854, and one of the most towering, honestly intimidating figures of Victorian science enters the narrative, Richard Owen.
Sir Richard Owen?
Richard Owen, the man who actually coined the word dinosaur. He decides to take a look at Mantell's supposed jawbone.
Owen was a brilliant, highly rigorous comparative anatomist. He looks at specimen R2239, he reads Mantell's description, and he applies a much stricter standard of evidence.
He wasn't one to just agree to be polite.
Definitely not. Owen says essentially, Mantell, your anatomical interpretation isn't impossible. It could theoretically be a quadrate bone. But then Owen points out a massive fundamental flaw in Mantell's logic regarding what animal it actually belonged to.
Because they didn't actually find the bone next to the teeth.
Precisely. This is such a vital moment in the development of paleontological methodology. Owen introduces the strict requirement of direct association.
The smoking gun.
Right. He notes that this bone was found isolated. It was not articulated with an iguanodon skull, nor was it found lying directly next to definitive iguanodon teeth.
And without that smoking gun, Owen basically says, we can't just assume they go together just because they lived in the same zip code.
Correct. Owen argues that the early Cretaceous ecosystem of the Wealden Formation was likely complex and diverse. It wasn't just Iguanodon walking around out there.
So what did Owen think it was?
Owen suggests alternatives. He says, since we don't have direct association, this bone might just as easily belong to another massive reptile we know from the era, like Streptospondylus, or perhaps Pterosaur.
Pterosaurs. Wow.
A massive crocodile-like marine reptile, or at least so they thought at the time.
It is such a great example of the scientific method in action, though. Owen is pulling back on the reins of assumption. He is introducing doubt where Mantell had certainty.
It's good science.
But the incredible irony here is that while Owen is being so incredibly careful about which animal it belongs to, both he and Mantell are still completely spectacularly wrong about what part of the body they are even looking at.
Completely wrong.
They are having this high-level, serious academic debate about whose jaw joint it is, and it isn't a jaw joint at all.
Not even close. Which brings us to a major paradigm shift. For decades, this bone just sits in the literature as a questionable skull fragment. It takes fresh eyes and a completely different specimen to finally crack the code.
And this is where the story truly explodes. We move to the year 1870. Enter a scientist named Harry Govier Seeley.
Seeley is a key player here.
Now, Seeley isn't looking at Mantell's original bone from the Tilgate Forest. He is looking at a new but strikingly similar specimen that was found on the Isle of Wight.
The Isle of Wight is another incredibly rich fossil locality just off the south coast of England. It features the exact same early Cretaceous deposits as the mainland Wealden Formation.
So it's a sister site, essentially.
Basically, yes.
Yeah.
The British Museum had actually purchased this particular specimen back in 1853, again from Mantell's expansive collection, but it had just been sitting there in a drawer until Seeley finally gave it a thorough, rigorous examination in 1870. It was cataloged as NHM UK PVR 28632.
Okay, so Seeley puts this massive rock on his desk. He compares it to the drawings and descriptions of the first bone, and he has an absolute eureka moment. What does Seeley see that Mantell and Owen completely missed?
Seeley possesses a very different perspective on comparative anatomy. He looks at this Isle of Wight specimen, and he immediately realizes they are not looking at the jaw. They are not looking at the skull at all.
What are they looking at?
These massive, heavy, block-like bones are vertebrae. They are the individual segments that make up the spinal column of a gigantic animal.
That is a massive course correction, from the head all the way down to the back.
It changes everything about how you orient the fossil.
But it goes deeper than just moving from the head to the back, right? Seeley also solves the mystery of the ear cavities that confused Mantell.
Yes, and this is where Seeley's genius truly shines. Remember Mantell's tympanic cavities? The spaces he thought housed the middle ear.
Right, the ear holes.
Seeley looks at those exact same indentations and hollows, but because he knows he is looking at a vertebra, specifically the centrum, which is the solid cylindrical main body of the vertebra, he realizes those openings aren't for hearing. They are entry points.
Entry points for what?
Entry points for a complex system of air sacs. Seeley realizes that the bone is not solid. It has been invaded by pneumatic cavities. The massive vertebra is essentially hollowed out from the inside.
Here's where it gets really interesting. I really want to make sure you listening grasped the magnitude of this discovery. When paleontologists say the bone is pneumatised or filled with cavities, don't just picture a hollow plastic straw.
No.
Think of the internal structure of a modern commercial airplane wing. Or think of a dense, intricate honeycomb. It is a highly complex web of bony struts and incredibly thin walls.
Nature's engineering.
Exactly. It is an engineering marvel designed to maintain immense structural strength and hold literal tons of weight while being composed mostly of empty air. And Seeley looks at this ancient, supposedly primitive reptile and sees this advanced engineering.
It was an astonishing revelation. Because in 1870, there were only a few places in the animal kingdom where anatomists had seen that specific type of internal weight-saving architecture.
Where?
In the bones of flying reptiles, the pterosaurs, and in the bones of modern birds.
Which explains the name. This is why Seeley names his 1870 paper and the new genus Ornithopsis bird-likeness.
Exactly.
He names the species Ornithopsis hulkei to honor his colleague John Whitaker Hulke. But Seeley doesn't just stop at a cool name. He actually takes a massive, incredibly bold theoretical swing based on this hollow bone.
He does. Seeley looks at the pneumaticity, the bird-like air sacs invading the spine of this terrestrial giant, and he proposes a wild evolutionary hypothesis. He suggests that Ornithopsis might represent a transitional link.
A transitional link.
He theorizes it's a bridge between the flying pterosaurs and modern birds, and that it is allied with the dinosaurs.
I mean, imagine dropping that theory into a Victorian academic society.
It would not go over well.
You have these scientists who are entirely accustomed to viewing ancient reptiles as sluggish, heavy, solid-boned, swamp-dwelling monsters. And Seeley stands up, points to a bone the size of a tree trunk, and says, "Actually, gentlemen, its spine is built exactly like a sparrow's. It's an evolutionary stepping stone." It completely upends the established worldview.
It was a brilliant, incredibly forward-thinking piece of anatomical deduction. But, as you alluded to, it was deeply unpopular with certain factions of the scientific establishment, suggesting that a massive, earthbound reptile shared such an intimate, sophisticated anatomical connection with birds.
It was a bridge too far for many.
And nobody hated a bridge too far more than Richard Owen.
Oh, Owen was furious.
Which brings us to the Great Retaliation. Let's look at the years 1875 to 1876.
It is really important to understand Richard Owen's position at this time. He was not just a scientist, he was an institution.
Right, he was superintendent of the natural history departments of the British Museum. Yes. He wielded immense influence over how both the public and the academic world understood these extinct creatures. And he was notoriously territorial, and often staunchly opposed to the emerging evolutionary theories of Darwin and his contemporaries like Seeley.
So it's 1875. Owen has had 5 years to stew over Seeley's Ornithopsis paper. 5 years of letting it bother him. Owen decides to revisit the fossils himself.
Time to set the record straight, in his mind.
Right. He publishes a new assessment. Now, Owen isn't foolish. He does concede one major point to Seeley. He looks at the bones and admits, okay, fine, they are vertebrae. Mantell and I were wrong about the jaw joint.
Which is big of him, I suppose.
But that is the absolute limit of Owen's graciousness.
Oh, absolutely.
Yeah.
Owen violently rejects the biological implications of Seeley's work. He outright refuses to accept the bird connection.
So how does he explain the hollow bones?
Owen looks at the extreme hollowing of the vertebrae, the very feature that defines the specimen, and he essentially dismisses it. He argues that this bone is much closer to a different genus of dinosaur that he, Richard Owen, had recently discovered and named Bothriospondylus.
Of course. It has to be related to his discovery. Let's track the academic pettiness here because it is just staggering. Owen decides that since Seeley's evolutionary theory is wrong, Seeley's name for the dinosaur must also be completely eradicated.
A total scorched earth policy.
Owen starts a massive renaming campaign. He looks at Mantell's original bone from the 1830s, the one he looked at in 1854, and he officially names it Bothriospondylus elongatus. He brings it into his own newly created genus.
And then he turns his sights on the Isle of Wight specimen, the exact specimen that Seeley had formerly named Ornithopsis hulkei 5 years prior.
Owen completely ignores Seeley's established name. He looks at the Isle of Wight vertebra and declares its new name is Bothriospondylus magnus.
It's astounding.
He even gives them 2 different species names, elongatus and magnus, refusing to admit the 2 bones belong to the same type of animal.
This is a blatant violation of the rules of scientific nomenclature, even as they existed then. The principle of priority dictates that the first formally published, validly described name for an organism is the one that stands. Seeley's Ornithopsis hulkei had clear priority.
So how does Owen justify steamrolling over the rules? I mean, he's the head of the museum.
He justifies it through sheer authority and personal disbelief. Owen wrote a scathing critique where he explicitly attacked the very premise of Seeley's name. Because Owen refused to believe that the vertebrae of these massive dinosaurs were open and lightly constructed like a bird's, he declared that the name Ornithopsis bird-likeness was, and I quote, glaringly false.
Glaringly false. He is literally saying, because I personally do not believe your anatomical theory, your validly published scientific name is a lie, and therefore I am legally allowed to rename it after myself. It is breathtaking arrogance.
It is the ultimate flex of institutional power. Owen is trying to rewrite the scientific record to align with his own philosophical view of what a dinosaur should be.
And the saga doesn't even stop there, right? In 1876, just 1 year later, Owen changes his mind again about the Isle of Wight specimen.
Wait for it.
The one he just named Bothriospondylus magnus.
Yes. He decides it doesn't belong in Bothriospondylus anymore.
You have got to be kidding.
He creates yet another genus, Chondrosteosaurus, based on some different Wealden fossils. And he arbitrarily moves Seeley's specimen into this new genus, renaming it Chondrosteosaurus magnus.
So let me get this straight. Within a span of 6 years, the single hollowed-out piece of spine has been called Ornithopsis hulkei by Seeley, then Bothriospondylus magnus by Owen, and then Chondrosteosaurus magnus by Owen again.
Yeah.
If you are a paleontologist trying to research this animal in the 1870s, you are pulling your hair out. It is a completely artificial taxonomic crisis created entirely by one man's ego.
It perfectly illustrates that taxonomy is not merely a sterile filing system. It is a battlefield. It is heavily influenced by the personalities, the rivalries, and the theoretical biases of the people holding the pen. Owen used his immense prestige to try and bury a genuinely brilliant anatomical insight simply by throwing a mountain of new invalid Latin names on top of it.
But history and science usually have a way of catching up to the truth. Owen's aggressive renaming campaign couldn't hide the physical reality of the bones forever. Which brings us to the cleanup crew. Let's move to 1879 and talk about a man named John Whitaker Hulke.
John Whitaker Hulke. He's a fascinating figure. He was a highly respected surgeon and a paleontologist. And importantly, he is the very man that Harry Seeley honored when he coined the species name Ornithopsis hulkei.
So Hulke clearly has a vested interest in this fight. It's his name on the line, too.
Exactly.
He steps into the ring to sort out the absolute mess Owen made of the Wealden sauropod fossils. What is Hulke's approach here?
Hulke takes a methodical, purely anatomical approach. He doesn't get into the philosophical weeds. He sits down with all the material. Mantell's bone, Seeley's bone, Owen's new specimens, and he systematically dismantles Owen's arguments. First and foremost, Hulke publicly defends Seeley against the charge that the name Ornithopsis was glaringly false.
How does he prove Owen wrong? Does he argue the evolutionary theory?
No, he doesn't even need to touch the evolutionary theory. Hulke simply points to the physical rock sitting on the table.
The evidence.
Yes. He points out that regardless of whether you believe this animal is related to birds, pterosaurs, or is just a weird, unique dinosaur, the physical, undeniable reality is that the bone is deeply hollowed out. It is lightly constructed.
You can literally see the holes in it.
Right. The internal camellae, the air chambers, are physically present. Therefore, Seeley's descriptive observation was perfectly accurate, and Owen's claim that it was false was entirely baseless.
So Hulke completely validates Seeley's science, and by doing so, he triggers the strict rules of taxonomy to deal with Owen's invented names.
Exactly. This introduces a really important concept in taxonomy: junior objective synonyms.
Okay, for anyone listening who isn't a museum curator, walk us through how a junior objective synonym works in practice.
It goes back to that rule of priority we talked about. Think of it like trademarking a brand name. Seeley registered the trademark for this specific fossil in 1870 with the name Ornithopsis hulkei.
Right.
When Hulke scientifically reaffirmed that Seeley's work was accurate and valid, that locked the name in. So what happens to the names Owen came up with in 1875 and 1876 for that exact same piece of bone?
They get booted out.
Yes. Because they were applied to the identical type specimen after a valid name already existed, they automatically become invalid. They are junior to the original, and they describe the exact same objective object. Therefore, they become junior objective synonyms. They're essentially tossed into the historical wastebasket.
So Bothrius spondylus magnus, gone. Chondrosteosaurus magnus, gone. Owen's attempts to overwrite history are officially nullified. I have to say it is deeply satisfying to see the dry, bureaucratic rules of science used to perfectly counter academic bullying.
It brought much-needed order back to the classification. But Hulke didn't just stop at defending Seeley. He realized that this specific anatomical feature, the intense bird-like hollowing of the vertebrae, was actually a unifying characteristic for a lot of the fragmented giants found in the Wealden Formation.
So he starts bringing other lonely floating fossils into the Ornithopsis family.
Yes. He looked at other genera that had been named from the area. For example, he looked at a genus called Iguanodon, which ironically Hulke himself had named back in 1870 based on different vertebral fragments.
Wait, he named it himself?
He did, and he realizes those fragments share the exact same internal architecture as Ornithopsis. So he voluntarily sinks his own genus. He declares Iguanodon to be a synonym of Ornithopsis. He also looks at the rest of Owen's Chondrosteosaurus fossils and realizes they belong there too. He is consolidating a sprawling, messy group of fossils under one unified, anatomically justified name.
It sounds like Hulke is the undisputed hero of the story, cleaning up the timeline and making everything neat and tidy. But we are talking about Victorian paleontology. It is literally never that simple, is it? Even the cleanup guy makes a mess.
Oh, it is a brilliant example of how easily the literature can become tangled. In 1882, Hulke is publishing a new paper. He is describing some newly discovered pelvis material from the Wealden, which he assigns to a new species he calls Ornithopsis eucamerotus.
Okay.
But in the text of that paper, while trying to clarify the history of the genus, he makes a critical clerical error.
What does he do?
He casually suggests that Mantell's original bone from 1833 specimen R2239, the one they all thought was a jaw joint for decades, should be considered the definitive type specimen for the entire genus of Ornithopsis.
But wait, in 1879, he specifically wrote that Seeley's Isle of Wight bone was the type specimen. You can't just swap the anchor of a species halfway through your career.
You absolutely cannot. The type specimen is the irreplaceable gold standard. It is the physical, tangible anchor that the conceptual name is permanently tied to forever. If you change the type specimen, you risk destabilizing the entire definition of the species. Hulke's contradiction created a massive headache in the scientific literature. Researchers didn't know which bone officially represented the animal.
So how do they fix a mistake made by the guy who was supposed to be fixing the mistakes?
It required more paperwork and intervention from other heavyweights in the field. It wasn't until 1888 that a prominent paleontologist named Richard Lydecker, working in direct consultation with Harry Seeley himself, had to publish a formal, official correction.
They had to step in.
They had to put it in writing, stating unequivocally that Hulke's 1882 suggestion was an error and permanently designating Seeley's Isle of Wight specimen, NHMUK PVR 28632, as the sole, unalterable holotype for Ornithopsis hulkei.
It's like they had to issue a formal press release to the academic world. Please ignore the typo from 6 years ago. We are sticking with the original plan. It just highlights how delicate the scaffolding of scientific taxonomy really is. It relies entirely on meticulous record-keeping.
And everyone agreeing on the same rules.
Right, and that scaffolding is about to be tested again because once the name Ornithopsis is locked in and people realize what to look for, those hollowed-out vertebrae scientists suddenly start seeing Ornithopsis everywhere.
They do?
This leads us into a period of wild expansion. Let's talk about the sprawling species of Ornithopsis.
This era is characterized by a practice very common in early paleontology. The creation of what we call wastebasket taxa.
Wastebasket taxa.
Yeah. When a distinct new genus is established, like Ornithopsis with its highly pneumatic bones, there is a strong temptation to take any new, somewhat similar, fragmented fossil you find and just toss it into that established genus rather than taking the professional risk of naming an entirely new dinosaur.
So Ornithopsis just becomes the default bucket for giant hollow-boned thing.
Precisely.
And the first major addition to the bucket comes from a completely different geological era. Let's look at the Leeds discoveries in 1887.
So John Whittaker Hulke is back at it. He is examining a new collection of fossils, vertebrae, ribs, and pieces of a pelvis. These weren't found in the early Cretaceous Wealden rocks of the south. These were discovered by a collector named Alfred Nicholson Leeds, far to the north in the Eisbury Jurassic deposits of Northamptonshire.
And right away, there are massive red flags that this might not be the same animal, right?
The differences were profound. First, the size was staggering. The new Eisbury specimens represented an animal that was substantially larger and much more robustly built than the Ornithopsis from the Isle of Wight.
Okay, so bigger and beefier.
But more importantly, the geology was wrong. These new fossils came from the lower Calovian deposits of the Wealden Formation. That is the Middle Jurassic period.
So you have an animal that is way bigger, found in a totally different part of the country, and lived tens of millions of years earlier than the original Ornithopsis. And Hulke looks at that and says, yep, same genus.
He did. Despite the vast temporal and morphological gaps, Hulke prioritized the structural similarities he saw in the bones over the geological context. He named this massive Jurassic creature Ornithopsis leedsii, honoring the discoverer, Alfred Leeds.
Wow.
He also attempted to build out the family tree, placing this genus within a family called Atlantosauridae, suggesting it shared a close evolutionary kinship with another famous British sauropod, Cetiosaurus oxoniensis.
Placing a middle Jurassic giant into an early Cretaceous genus is wild. But what I find genuinely hilarious about the whole Ornithopsis leedsii situation is the absolute inability of subsequent elite scientists to spell the man's name correctly.
It's a running joke in the literature.
You have these brilliant minds publishing in the most prestigious academic journals of the era, and they just butcher it.
The taxonomic history of this specific specimen is completely riddled with typographical errors that became formalized in the literature. Hulke clearly named it leedsii with a double I at the end.
Leedsii.
Right. But in 1895, Richard Lydecker refers to it as Pterosaurs leedsii, dropping an I. A decade later, in 1905, Arthur Smith Woodward writes about it and calls it Cetiosaurus leedsii, also dropping the I.
It proves that typos and bad autocorrects have existed long before computers. But even through the typos, you can see the uncertainty. They are shifting it from Ornithopsis to Paleosaurus to Cetiosaurus. Nobody knows where this massive Jurassic beast actually belongs.
It's just getting passed around.
And the confusion isn't limited to the Middle Jurassic. Let's bring in another outlier, the Mansell humerus. This is a single, isolated arm bone found by J.C. Mansell back in 1868 in yet another distinct geological layer, the Kimmeridge Clay Formation, which is late Jurassic.
The Kimmeridge clay is really famous for marine reptiles, but occasional dinosaur remains wash in. Hulke examined this massive humerus in 1874. He recognized it belonged to a colossal sauropod, and he wanted to emphasize its strength. So he coined the name Ischyrosaurus, meaning strong lizard.
But the rigid rules of taxonomy strike again, and Ischyrosaurus gets shot down. Why?
It comes down to the absolute rule against homonyms in zoological nomenclature. You cannot have two different animals with the exact same genus name.
Makes sense.
Hulke tried to publish Ischyrosaurus in 1874, but he was entirely unaware that the prolific and famous American paleontologist Edward Drinker Cope had already utilized a remarkably similar name, Ischyrotherium, back in 1869.
Ah, Cope.
Yes, Cope used it for a fragmented fossil he initially thought was a mammal, but was later deemed a reptile.
So Cope beat him to the punch, and Hulke's name is locked out. The bone needs a new identity.
Yes. So in 1887, Richard Lydecker steps in to fix the nomenclature issue. Lydecker looks at this giant late Jurassic arm bone, and he decides to toss it into our rapidly expanding wastebasket. He renames it Ornithopsis mansellii.
So let's review the Ornithopsis family tree at this point. You have the original Ornithopsis hulkei in the early Cretaceous. You have the massive Ornithopsis leedsii in the middle Jurassic, and now you have Ornithopsis mansellii in the late Jurassic. It has become a meaningless catch-all term for a large British dinosaur with complicated bones.
Exactly. And the debate over that single arm bone, the Mansell humerus, is a perfect microcosm of how difficult paleontology is. That debate didn't end in the 1880s. It is still an active point of contention in modern literature.
Really? What are paleontologists saying about it today?
It is entirely unsettled. In 2006, researcher David Martill and his colleagues published a review where they actually chose to retain Lydecker's name, Ornithopsis mansellii, primarily because Hulke's original name was still blocked by Cope's prior usage. However, many of their peers strongly disagree. Some argue it should be grouped with a different sauropod genus, becoming Pterosaurus mansellii.
And others just throw their hands up completely, right?
Precisely. In 2004, Paul Upchurch and his team published a massive, comprehensive review of sauropod dinosaurs. They looked at the Mansell humerus and officially designated it a nomen dubium, a dubious name.
Dubious name.
Yes. They concluded that a single, isolated arm bone simply does not possess enough unique diagnostic anatomical features to definitively assign it to any specific genus. Further complicating matters, a 2010 study pointed out that the bone shares broad anatomical characteristics with two entirely different branches of the sauropod family tree, the Robocosauridae and the titanosauriforms. It sits right on the morphological fence.
It is the ultimate frustrating puzzle piece. It looks like it could belong to two different puzzles, but it doesn't quite complete the picture for either one.
A paleontologist's nightmare.
But wait, the Ornithopsis wastebasket wasn't just catching British fossils. To add one final layer of complexity, we have to talk about the Swiss connection. The name literally crosses international borders.
Yes, the confusion was exported. In 1921, an incredibly prolific German paleontologist named Friedrich von Heeren was studying dinosaur remains recovered from Jurassic deposits near Bern, Switzerland.
Switzerland.
Yeah. These deposits yielded a fragmentary but significant amount of material, including a long tail sequence. Owen looked at these bones and described them under the name Ornithopsis grappini.
And I love that he literally put a question mark in the official scientific name, Ornithopsis question mark. He is formally publishing his own hesitation.
The question mark is telling. It shows that even the author recognized the assignment was tentative at best. Owen was trying to find a home for these bones among the known European giants. But as he continued to study sauropod evolution over the next few years, his understanding shifted dramatically. By 1927, Owen published a major revision.
What did he decide?
He decided that the massive Middle Jurassic leedsii specimen from England and his new grappini specimen from Switzerland possessed too many distinct differences to remain in the Ornithopsis genus.
So he pulls them out of the bucket.
He does. He creates a brand new genus exclusively for them, which he names Cetiosaurus. So the Swiss material becomes Cetiosaurus grappini.
But the journey for those Swiss bones didn't stop in 1927. They recently got yet another update, right?
Indeed. It really demonstrates the iterative, self-correcting nature of the science. Nearly a century later, in the year 2020, a team of modern paleontologists conducted a rigorous, high-tech redescription of that original Swiss fossil material.
And what did they find?
Armed with a century of new comparative data and advanced imaging techniques, they concluded that the Swiss dinosaur was entirely distinct. It didn't belong in Ornithopsis, and it didn't belong in Sauropod. They finally gave it its own unique, independent genus name, Amansia.
I love that. From an unknown bone in 1921 to a tentative Ornithopsis to Sauropod, and finally, 100 years later, it stands alone as Amansia. It is a beautiful illustration of how science slowly, methodically whittles away the errors until it finds the truth.
It takes time, but it gets there.
So what does this all mean? Which brings us, at long last, out of the Victorian era, out of the wastebasket taxa, and into the stark light of modern science. Let's look at what we actually know today. When we strip away all the ego, the aggressive renaming, the typos, and the confusion, what is the physical reality of Ornithopsis hulkei? If a paleontologist walks into the Natural History Museum today and looks at Seeley's holotype specimen NHMUK PVR 28632, what exactly are they seeing?
When you look at the holotype today, completely divorced from all the historical drama, you are looking at an extraordinary piece of biological engineering. To be clear on what remains, it is a single vertebral centrum.
The main body of the bone.
Right.
Right.
It is missing the neural spine, the tall piece of bone that would stick up dorsally to anchor muscles. We only have the main cylindrical body of the vertebra. But that cylinder tells an incredibly detailed story.
Walk us through the anatomy. What are the key features that define this creature?
The most immediate and striking feature, the one Seeley originally noticed, is that it is intensely pneumatized. It is absolutely riddled with cavities. In modern paleontological terminology, we refer to these specific, complex internal chambers in sauropod vertebrae as camli.
Going back to our airplane wing analogy, it's that internal honeycomb structure.
Precisely. The presence of these extensive camli is definitive proof that the living animal possessed a highly complex respiratory system. It had air sacs that extended outward from its lungs and literally invaded the bones of its skeleton.
Just like modern birds.
Exactly. This served multiple critical functions. It drastically reduced the overall weight of the massive skeleton, allowing the animal to grow larger without collapsing, and it significantly increased respiratory efficiency, which is vital for a multi-ton animal to power its metabolism.
Okay, so we have the internal honeycomb. What about the external shape?
The external morphology is highly distinct. The vertebra is described as being narrow and tall. It shows what we call lateral compression. Running along the bottom surface, the underside of the bone, is a very prominent, distinct ridge, which we call a ventral ridge.
Narrow, tall, and a keel on the bottom. What else?
It is strongly opiscicoelous. This describes the articulation points, how the individual vertebrae physically connect to one another to form the spine. An opiscicoelous vertebra has a centrum that is deeply concave at the back end and strongly convex at the front end.
So they slot together like a massive ball and socket joint, giving the neck or back both strength and a degree of flexibility.
Exactly. You've got it. And finally, there is one more crucial external feature. On the side of the vertebra, there is a deeply inset, hollowed-out depression. This is called a pluricle. In the Ornithopsis holotype, this pluricle is subtriangular in shape, and it is massive. It extends over 2/3 of the entire length of the centrum.
So we have this laundry list of very specific traits. The honeycomb cameli, the narrow and tall shape, the ventral keel, the ball and socket joints, and this massive triangular hollow on the side. Why does all of this specific geometry matter? Does it actually prove anything, or is it just descriptive?
If we connect this to the bigger picture, it matters immensely because, in combination, those features are diagnostic. For a very long time, because the Wealden fossils are so fragmented and because the history of their naming was so chaotic, many modern researchers were inclined to just throw the entire genus out.
They just didn't want to deal with it.
Right. They considered the fossils too scrappy to be scientifically useful, labeling them as dubious or intermediate forms.
They wanted to put Ornithopsis itself into the wastebasket?
Yes. But in 1995, a researcher named William Blowes published a critical reassessment. He meticulously analyzed those specific traits. He demonstrated that the unique combination of the extreme lateral compression, the narrow and tall profile, and that specific ventral ridge are not just random variations. They are definitive, unique identifiers. Blowes confirmed that these traits prove the bone belongs to a distinct, highly derived titanosauriform.
So Blowes rescues Ornithopsis from obscurity. He clears away the dubious label and proves that Seeley's Isle of Wight fossil isn't just a generic piece of rock, it is a specific, scientifically valid animal. Ornithopsis hulkei earns its permanent place on the dinosaur family tree.
It finally gets its due.
But the incredible thing is, the story of Ornithopsis isn't just confined to the Isle of Wight or to the dusty archives of Victorian England. This 130-year-old anatomical debate actually has direct relevance to discoveries being made right now. Let's bring the timeline all the way into the present day.
It is a perfect demonstration of how historical paleontology continues to inform modern fieldwork. In 2023, a fascinating new paper was published documenting a recent discovery in northwestern Germany.
Yes. Paleontologists were excavating in an area called Balve. They are working in a limestone quarry that dates to the late Barremian to early Action stages. That puts it right in the sweet spot of the Early Cretaceous period, roughly the exact same age as the Wealden Formation in England.
Right.
And during this excavation, they uncover a fragmentary dorsal vertebra, a piece of a backbone.
And when the German paleontologists brought this bone back to the lab and cleaned it up, they didn't just see a generic sauropod fossil. They looked at the geometry of the bone, and they saw something distinctly familiar.
What did they see? Did it have the honeycomb?
It was more about the external morphology. The researchers noted that this new German specimen possessed a very specific shape. It shared the distinct lateral compression, the uniquely narrow and tall profile that William Blows and others had confirmed was diagnostic of Ornithopsis.
So they find a bone in Germany that perfectly matches the architectural blueprint of the bone from the Isle of Wight.
Precisely. Because of that shared, highly specific diagnostic trait, the researchers formally referred the new German specimen to the genus Ornithopsis. However, in their publication, they listed it as Ornithopsis make.
And there is that question mark again. Why the hesitation this time? Why not just call it Ornithopsis hulkei and be done with it?
The S-make is a crucial piece of scientific shorthand. It stands for species uncertain. The researchers are making a very careful, calibrated statement. They're saying, based on the distinct lateral compression we can observe, we are confident this bone belongs to the genus Ornithopsis. However, the preservation of this specific fossil is too poor, or it is missing too many other key features for us to confidently assign it to the known British species, O. hulkei, or to justify naming a brand new German species.
It's the modern equivalent of Owen's skepticism, but applied correctly. They are saying, this is our best, most educated hypothesis based on the morphological evidence we have right now, but we are waiting for better, more complete material before we etch a new species name in stone.
Exactly. It is scientific rigor in practice. And despite the fragmentary nature, the discovery itself is highly significant.
Because it completely changes our understanding of where these animals lived. We went from a single dinosaur isolated on the Isle of Wight to realizing that these massive bird-boned titanosauriforms were roaming across a massive swath of what is now Europe.
A huge geographic expansion.
And based on the size of the vertebra found in Balve, the researchers estimate this specific German individual was slightly smaller than the massive 16 to 18 meter giants from Britain. But it proves they were an established, widespread part of the early Cretaceous ecosystem.
It connects the dots.
And I think that incredible geographic leap is the perfect place to wrap up our deep dive today. Let's take a step back and look at the sheer scale of the story we just traced.
It's quite a journey.
We started all the way back in 1833, in the muddy Tilget Forest, with Gideon Mantell holding a hollowed-out piece of spine and completely understandably, but totally incorrectly, guessing it was the jaw joint of an Iguanodon. We watched Richard Owen apply a rigorous standard of evidence to disprove Mantell, only to completely fail to recognize what the bone actually was himself. We witnessed Harry Seeley's brilliant stroke of insight in 1870, looking at those cavities, realizing there were air sacs just like a bird's, and coining the name Ornithopsis.
And then we saw the scientific process briefly derailed by human ego. We watched Richard Owen throw a taxonomic temper tantrum, aggressively inventing names like Bothriaspondylus and Chondrosteosaurus, simply because he found the idea of a bird-like giant reptile philosophically offensive. We saw John Whitaker Hulke step in to act as the referee, using strict rules of nomenclature to toss Owen's names in the bin, even as Hulke made his own clerical errors along the way.
We tracked how the name Ornithopsis ballooned into a wastebasket for massive bones from entirely different geological eras, from the Middle Jurassic of England to the Late Jurassic of Switzerland, before modern analytical techniques slowly, systematically pruned those eras away. And finally, we arrived at the modern day, where that heavily debated, much maligned piece of Isle of Wight bone is recognized as a vital key to understanding an entire lineage of 16-meter-long, air-filled titans that roamed from Britain to Germany.
If there is one overarching takeaway from this entire saga, it is that science is fundamentally, unavoidably, an iterative process. It is a long, winding journey, not a sudden arrival at absolute truth. It requires critical thinking. It requires individuals like Seeley being willing to look at a structure that everyone else assumes is a tympanic cavity and ask, what if we are all wrong? What if that is an air sac?
You have to question the baseline.
Exactly. And crucially, it requires the humility to constantly refine and overwrite our understanding as new data, like a fragmentary bone pulled from a German limestone quarry in 2023, emerges to test our models.
Science is undeniably messy because it is conducted by humans. We have egos, we make typos, we hold on to outdated philosophies. But the beauty of the scientific method is that over decades, and sometimes over centuries, it slowly self-corrects. The ego fades away, the junior synonyms get deleted, and the physical truth of the animal remains.
Well said.
And before we let you go, I want to leave you with a final lingering thought to mull over. We have just spent the last deep dive tracing how a single genus, Ornithopsis, spent nearly a century bouncing between completely different identities. It was called a jawbone, it was called Bothriospondylus, it was called Chondrostriosaurus, and its cousins were called Cetiosauriscus and Amansia. And all of this confusion happened simply because the fossil evidence was fragmentary and the scientists looking at it couldn't see the big picture.
They only had a few puzzle pieces?
Given that incredibly messy history, I want you to think about the natural history museums of the world right now. Think about the millions of fragmented, unsorted, or hastily categorized fossils sitting in dark, dusty drawers in London, Berlin, New York, and Paris. How many completely undiscovered, missing branches of the dinosaur family tree are sitting in those drawers right now, mislabeled with a name coined by a Victorian scientist who was just taking a wild guess? How many spectacular new species, how many paradigm-shifting ancient monsters are just waiting in the dark for a modern-day Harry Seeley to open the drawer, look at the bones with fresh, unbiased eyes, and completely rewrite the history of life on Earth?
Now that is something to think about.
Thanks for taking the plunge with us. Keep questioning, keep digging, and we will see you on the next deep dive.